All right, so we're going to continue our discussion today with applications of the Chebotarev density theorem. But first, I want to address a couple of points that came up last time, or that I'm just going to make up as if they came up last time. So one question that did get asked was, to what extent the proof of Chebotarev density theorem needs class field theory, which is general theory of abelian extensions of number fields. And nowadays, usually a proof of Chebotarev density theorem will rely on results from class field theory, the art and reciprocity law, or things around that set of ideas. But Chebotarev himself proved his theorem over the rational numbers before class field theory was kind of understood as a coherent subject, and his ideas actually helped Artin in the development of like the art and reciprocity law. So, so class field theory is definitely not needed. At least if you wanted to prove the Chebotarev density theorem, let's say over the rational numbers, or maybe even over a number field. But if you wanted to find a reference on that, most books, if they have a proof of the Chebotarev density theorem, it'll be after some development of class field theory. So if you want to see references that have a proof not using class field theory, then let's just say CFT. That does not mean conformal field theory or anything else. So two places I found is you could look up, there's an article on the Chebotarev density theorem by Lenstra and Stephenhagen. So if you just Google Chebotarev Lenstra or Chebotarev Lenstra Stephenhagen, then you can find it. This is I think 1996, and in the appendix they outline a proof that does not rely on class field theory. It uses composites with choices of cyclotomic extensions of various number fields, even over a general base field. And that was kind of Chebotarev's key idea that then Artin used for the art and reciprocity law. So that kind of use of cyclotomic fields is present in all proofs. But it does not require developing all the machinery of class field theory. Another reference is there's a book by Fried and Yarden called Field Arithmetic. And if you look in, chapter 5 of the first edition or chapter 6 of the second edition, the title of the chapter is Chebotarev density theorem. So it's hard to miss. And so those are two places. But this book, because they really start from scratch, I mean, it's a huge, long slog. But anyway, they also use cyclotomic extensions, but they don't rely on any general procedures of class field theory. Okay. The other thing I wanted to bring up, which I haven't really talked about here, although I referred to it in the notes from the first day, is the issue of the way that we're computing the density of the primes. So if we wanted to calculate, or maybe I should really say define, the density of a set of primes, what should we call it? Say script P of primes. I'll just work with prime numbers. Everything I say could be adapted to prime ideals in a number field. So one way, and the way that I've been presenting things, is in terms of what I call the natural density. Call it delta n of your set of primes. And it's defined, well, the reason for the word natural is you just count. You count the primes up to x that are in your set and divide by the total number of primes up to x and take the limit. And if that exists, that's called the natural density of your set of primes. And this is the one that I used when I was discussing the Chebotarev density theorem or Dirichlet's theorem. The natural density of, you wanted to calculate the natural density of the set of primes that are congruent to 3 mod 10 is 1 over phi of 10, or 1/4. and the Chebotarev density theorem. If P is the set of primes in Z that have a given Frobenius conjugacy class and some Galois extension of Q, then that limit, the natural density exists as the size of the conjugate class over the size of the group. So there are other notions of density. There's the Dirichlet density. It's the one that Dirichlet used when he proved his theorem on primes in arithmetic regression. We'll call it delta D of P. And this is a very non-intuitive thing. It's another limit, but instead of counting the primes up to some bound that are in the set of interest as a proportion of all of them, it's a totally different kind of limit. You introduce a variable S, you sum over the primes in your set, not 1 each time, but 1 over P to the S. So you take the infinite series over all the primes in your set of 1 over P to the S divided by the sum over all primes of 1 over P to the S. And that ratio, as S tends to 1, you take that limit. This has absolutely no intuitive meaning. But if the natural density exists, then this other density exists and they're equal. You could have, maybe I'll present the third one before I make comments about how these are related to each other. And then we have another one called a logarithmic density. How do you think we should write this one? How do you think I should denote it? Delta sub L. If only you could see my notes, you would see I wrote delta sub L. And so now we're going to take, it's going to again be a limit, but instead of weighting each prime by 1, if it's in the set of interest, we're going to sum over P up to X that are in our set, and we're going to weight each P with 1 over P and divide by the sum over all P up to X, 1 over P. So another ratio, if I was just summing with a weighting factor of 1, this would look like the natural density, but this is something different. So how are these all related to each other? So first of all, the Dirichlet density and the logarithmic density are actually always the same. If one exists, the other exists, and they're equal, or maybe none of them neither one exists. This is not obvious. Another one is that if delta n exists, then the other densities are equal to it. But the converse is false. You can have a set with a Dirichlet density or logarithmic density, but not a natural density. And the usual example that's found in all the books, I mean, you're not going to find it in Harry Potter, but when they discuss Dirichlet density, you often see this caveat that if you have a set that has a Dirichlet density, it might not have a natural density. And the usual example given is all the primes that have, in terms, it's a base property, all the primes P such that the decimal expansion of P, say, starts with some digit D, 0 to 9. So this has a Dirichlet density log base 10 of D plus 1 over D, but the natural density does not exist. The reason is that, as you might imagine, the primes that start with a 1, there's a big chunk of them, but then they disappear for a long time as the count of actual primes accumulates. Then they suddenly start to show up again, right? You're going from 10 to 19, and you have nothing. You're counting until you hit 100 to 199, and then nothing until you hit 1,000 to, and so forth. Meanwhile, so the counts kind of jump around a lot. So there's no natural density, but it turns out there's a logarithmic or Dirichlet density. In particular, the primes that start with a leading digit of 1 have a Dirichlet or logarithmic density log base 10 of 2. Okay, so yes, where's there a question? Yes, so if you've heard of Benford's law, this is a Benford-esque property, but it's actually a proof. It's not experimental Yeah, so there's no, I'm sorry? No. The proof of this has absolutely no dependence on the prime number theorem or anything like that. It's just a totally separate calculation. And it's not so easy to find this calculation in the literature, right? Books will say, well, there's this example, Bombieri once showed Serre that the primes of leading digit of 1 have Dirichlet density log base 10 of 2. But it's like, but where's the proof? Okay, so I'll tell you where the, so if you want to see a calculation that the log density is this, you can go see Math Overflow question 278209. It's there. I wrote it. Okay, so I mean, the thing was, it puzzled me for a long time and then finally I found and looked up a reference and figured, oh, that's what happened. And I was like, I don't want to forget this. So then I went back to the Math Overflow question and answered it. All right. Anyway, but notice to show the log density has this value, it's one thing. Then there's also the detail of why is logarithmic and Dirichlet density, why are they the same thing? They don't look anything alike, and that's its own kind of lengthy argument. But in any case, there it is. So that's an example. Does not exist. Ugh, does not exist. Okay. So in any case, the main important difference between these types of densities, well, there's no difference between items 2 and 3, it turns out. The real difference between, say, 1 and 2, natural density and Dirichlet density, is in the actual proof that, say Chebotarev or Dirichlet's theorem, that some set of primes has a specific natural density or Dirichlet density. The technique of proof is fundamentally more complicated for 1 than for 2. So the big contrast, excuse me, the big contrast of natural density versus Dirichlet density in proofs, if you ever look at a proof of like the proof of Dirichlet's theorem, it's that for the Dirichlet density, what you usually use is you're going to use Dirichlet series of some type, an over n to the s, when s approaches 1. And for natural density in the proofs, you're going to use a Dirichlet series on the entire line, real part equals 1. So in some sense, you have to understand the behavior of a Dirichlet series near a certain point around the point 1 in order to calculate Dirichlet density. Not a surprise. Look at the very definition of Dirichlet density. It's a limit as s goes to 1, and it involves Dirichlet series near the number 1. Natural density has no mention of Dirichlet series anywhere in it, so it's already a hard argument to make a connection between those. But when you do, in practice, natural densities for sets of primes usually involve some kind of a calculation of a Dirichlet series on the entire line. And so you kind of require much more information. So to compute a natural density requires much more work, okay, when they both can be computed. All right. So I want to discuss, coming back to now, Frobenius elements and Chebotarev. I want to talk about how Frobenius elements are related in a Galois group, are related to permutations of the roots. So now we want to, in a Galois extension, and I'll just work with the base field, the rational numbers for simplicity. Everything I say could be jazzed up if you so wish. So in a Galois, in a finite, in a Galois extension, we want to relate a Frobenius element in the Galois group to, let's say, a permutation of the roots of a polynomial when you have a polynomial where K is the splitting field. So first, let me just so I guess I'll state the basic theorem here. Yeah. So here's the basic theorem. It goes back to Dedekind. So we start off with the Galois extension, and we write it with a primitive element. I'll say K is Q adjoint alpha. So we pick an element that generates the entire field. With alpha will be an algebraic integer, and f of x will be its minimal polynomial. The minimal polynomial, this came up in a discussion with some students at the board on the first day. The minimal polynomial of an algebraic integer will always be monic with integer coefficients. That's not a sentence. Then what we want to do is, so if we have this set up, and we have a prime number that does not divide the discriminant of the polynomial, I'll remind you what the discriminant is in a moment, then the polynomial will reduce mod p to a product of distinct irreducibles, say distinct irreducible pi j's monic irreducibles, and if we take the Frobenius element for any prime ideal that divides P, it acts on the roots of the polynomial as a permutation whose cycle structure, is this still one sentence? K is Galois, K is Q alpha with alpha and OK, and F is middle polynomial over Q, and P is a prime such that P doesn't divide the discriminant, comma, pause. Then F decomposes for some distinct irreducibles, mod P, and the Frobenius element in the Galois group for prime ideal, any prime ideal dividing P, acts on the roots of F of X as a permutation with cycle type D1 through DR, where the D's are the degrees of the irreducible factors of F mod P. Period. Finally. So that's a theorem. What is it saying? Let me show you some examples. So let's take the polynomial x to the 4 minus 2. Right? Oh. So my very long sentence needs to be corrected. I should have started with the polynomial. Should have taken the polynomial first. If we have a monic polynomial and K is its splitting field, so we might not start with a polynomial where a root of it generates a Galois extension, like x to the 4th minus 2. So you have a polynomial in Zx, monic, and K is its splitting field over Q. Why am I trying to be fancy here to move? So cool. All right. So we have a polynomial monic over the integers, K is its splitting field over Q, and P is a prime that doesn't divide the discriminant. then our polynomial will break up for some distinct irreducibles, period. Oh, look, the sentence got shorter. So now, if we write, let alpha be a root. Oh no, I don't have to. Okay, so for any prime ideal, the dividing p in OK, the Frobenius element, it turns out to make sense. There's no ambiguity in this case when p is a prime not dividing the discriminant, and so this Frobenius element acts on the roots of f of x as a permutation with cycle type. I don't know how you're making the edits, but this is kind of neat. Okay, period. Let's bring this up a little bit. Okay. So is anybody taking notes on a tablet? Yeah, okay, so great. All right, so here we have a polynomial. It's splitting, oh, I'm sorry, excuse me. I meant to, let's push this back down. So I'm just, recall it, when you have a polynomial that breaks up roots alpha 1 through alpha n, the discriminant of the polynomial is the product of the differences of the roots all squared, taking products over distinct indices, okay? So this is going to be a non-zero integer when f is irreducible in z bracket x. And so it may or may not have, in fact, it will have prime factors. There's no irreducible in z bracket x, non-degree bigger than 1 that has discriminant, whatever. All right, so what's the splitting field in this case? I need a 4th root of 2 and a primitive 4th root of unity that for some reason I'll call I. So, so in this case, what I'm saying, what Dedekind's theorem is saying is if you decompose x to the 4th minus 2 modulo a prime number, as long as you avoid the prime 2, so this discriminant is minus 2048. Does anybody know the prime factorization of 2048? 2 to the 11, very good. Whatever happened to that game? Still play. I feel like Wordle just like took it over. I hadn't heard it. Wow, I haven't heard of 2048 in such a long time. I can play it on an Emirates flight. Yeah. I've never been on Emirates in my life. Now I'm motivated to look for Emirates. If I actually haven't flown in 3 years for some reason. All right. So so what it's saying is for odd primes, if we know how. So let me show you how x to the 4th minus 2 mod p decomposes for several odd primes. 3, 5, 7, 11, 13, and 17. So in degree 3, it breaks up x squared plus 3x plus 2 times x squared plus 2x plus 2. Degree 5, it's irreducible. In degree 7, it has 2 linear factors and 1 quadratic factor. Can anybody see why, as soon as this polynomial has 1 root, it must have a second root, mod p? If you look at the polynomial, x to the 4 minus 2, if it has a root in z mod p, why it must have a second root in z mod p? Yeah, right? As long as p is odd, 0 won't be a root. So if you have a root, a mod p minus a will also be a root. So the fact that we've got 1 linear factor, the other one, x 2 and 5, oh, look, they're negatives mod 7, not a surprise. So it will not decompose as a linear times a cubic in its irreducible factorization. Mod 11, we have x squared plus 4x plus 8 times x squared plus 7x plus 8. Mod 13 is irreducible, and mod 17 is another quadratic factorization, but you don't have any linear, the linear coefficients are 0. And so what Dedekind's theorem is saying is if you look at the, I'll put down here what I'll call the degree type of the factorization. It's the degrees of the irreducible factors. So I'm just listing the degrees of the irreducible factors. When it's irreducible, you have a single degree 4 irreducible factor. So here we have some degree types. How many roots does this polynomial have? It has 4 roots, the 4 different fourth roots of 2. And something you see in group theory when you deal with symmetric groups and permutations is a permutation has a cycle decomposition, right? You have a permutation of n things and it breaks them up into disjoint collections, and you see how long those lengths of those orbits are, and that's the cycle structure of the permutation. And so what Dedekind's theorem is saying says that in the Galois group of K over Q, there are permutations of the roots, of the 4 roots of x to the 4 minus 2. That was a pretty bad 4. Of x to the 4 minus 2 with these degree types as the cycle type. Meaning, for example, there is a permutation of the 4 roots that puts them in pairs, an orbit of length 2 and an orbit of length 2. There's a permutation in the Galois group of K over Q that's a 4 cycle, or that's a 2 cycle, right? The thing mod 7, a permutation of type 112, degree type 112 must appear as a, oh, excuse me, I got ahead of myself. So Dedekind's theorem is saying that the Frobenius element at a prime dividing P will have the cycle type that matches the factorization with those degrees. And so it's saying that a Frobenius element at 7, so for example, more specifically, if P divides 3, the Frobenius element at P permutes the roots with as a permutation of the 4 roots of x to the 4 minus 2 with cycle type 2, 2. And if P divides a prime dividing 7 in the ring integers of x of the splitting field, it's the Frobenius element will permute the roots as a 4 cycle. Because x to the 4 minus 2 is irreducible mod 7. There's this relationship between how the polynomial factors mod P and how the Frobenius element at a prime ideal dividing P in the Galois closure in the splitting field of the polynomial, how it permutes the roots. Degree type, cycle type, they match up. At primes that don't divide the discriminant. We're not saying at the primes that divide the discriminant it can't work, but it's not guaranteed, and so we don't worry about it. So does anybody know from Galois theory what is the Galois group of K over Q? Maybe we talked about this before. Q join the 4th root of 2 and I, yeah? Oh yeah, absolutely. What did I say, 7? Yeah. P divides 5. Yes, sorry about that. Yeah, right. So 5 is irreducible. 5, we get the 4 cycle. And 3, we get the cycle type 2, 2. Right? So when you apply a Frobenius at a prime ideal dividing 3, you have the 4 roots, and it'll link 2 of the roots and 2 other roots. Kind of like, well, so complex conjugation will fix the real 4th roots of 2 and swap the 2 non-real 4th roots of 2. So maybe the Frobenius at 7 would be like complex conjugation, perhaps. Okay. So, what? Anybody know what is the Galois group of K over Q in this example? Right, the dihedral group. So this Galois group is isomorphic to D4, and it's going to be generated by two elements, R and S, where R, everything is determined by what you do to the 4 through the 2 and I. So 4 through the 2 will go to I 4 through the 2, and it will fix I, and S will fix the 4 through the 2. S is like complex conjugation, and it will negate I. So there are 8 automorphisms, and everything's built out of these 4 things. So R has order 4, S has order 2, and SR is R inverse S, or R cubed S. Okay, it's a dihedral group of order 8. So, so if I were to say, well, so what are the how do these things behave on the 4 roots? So, for example, I think we discussed this example yesterday and saw R is a 4 cycle on the roots, right? So R is a 4 cycle on the roots of x to the 4 minus 2. Saw that yesterday. And S is a permutation of the roots of type 1, 1, 2, because it fixes 2 of the roots. They stay fixed, and it swaps the other 2. All right. So what are the conjugacy classes? Maybe I should say, if we list the roots, let's list the roots. 4 through the 2, I think we did this yesterday. I 4 through the 2, minus 4 through the 2, minus I 4 through the 2. So here's a root, and we'll label them as 1, 2, 3, and 4. And so then R looks like the 4 cycle 1, 2, 3, 4. R squared, if you square it, it becomes 1, 3, 2, 4. R cubed is 1, 4, 3, 2. R to the 4th is the identity. S fixes 4 through the 2 and minus 4 through the 2, fixes 1 and 3 and swaps 2 and 4. And I guess, what else do I want to write down here? RS, you can check, is a 1, 2, 3, 4, cycle type 2, 2. R cubed S also is a cycle type 2, 2. It's 1, 4, 2, 3. So we met all possible permutations on 4 things, the cycle type 2, 2. And I'm just missing the identity. And what else am I missing? I'm missing R squared S. R squared S is 1, 3. Okay. So the conjugacy classes, I didn't write down the identity. The conjugate classes, you have the identity, you have R squared, it's in the center, it's its own conjugacy class. R and R cubed, S and R squared S, and RS and R cubed S. So these are the conjugacy classes. And so let's, if we look at these, the way they permute the roots, different elements in the Galois group permute the roots in different ways, except the ones I highlighted, R squared and RS and R cubed S. Those are 2 different conjugacy classes that permute the roots in the same way as abstract permutations. They are conjugate in S4, they're not conjugate in D4. R squared is different from RS and R cubed S. So if we look at our table, we see that there are 3 examples at the prime 3, at the prime 11, and at the prime 17. In those cases, we can't tell. Dedekind's theorem is telling us that the Frobenius elements at a prime ideal, dividing these primes, must permute the roots in a way whose cycle type is the degree type. So we could say, like, the Frobenius at 5. So from the table, of factorizations of x to the 4th minus 2, if p divides 5, the Frobenius element, because it's irreducible, cycle type is just a 4 cycle, this Frobenius element is R, or R cubed, and those are conjugates. So the Frobenius conjugacy class of 5 is R and R cubed. We actually saw this yesterday. We worked out that a Frobenius element at 5 must permute the roots as a 4 cycle. And now we see that's actually related to the fact Dedekind's theorem is telling us it's because the polynomial x to the 4 minus 2 is irreducible mod 5. Okay, but if we looked at the case of 3 or 11 or 17, if p divides 3 or p divides 11 or p divides 17, it's not a little obvious which Frobenius conjugacy class is this going to be equal to r squared, or is it going to be one of r squared has type 2, 2, and the other ones of type 2, 2 are rs and r cubed s. It's not clear, right? Which way does it go? So you can have non-conjugate elements in the Galois group that permute the roots of the polynomial that generates the field with the same abstract cycle type. It's like, how do you tell the difference? So is there something we can say about these? As permutations, they kind of look indistinguishable because as elements of S4, they're conjugate there. So in D4, they're not. How can we tell the difference? Because of where they're coming from, if we take advantage of the formulas, R fixes S, R fixes I, see at the top of the slide, R fixes I, and S negates I. So one thing that we can say is that R squared fixes I because R fixes I. And, oh, wow, I lost track of time. And on the other hand, RS negates I, and R cubed S negates I. So that's the difference. And how can we take advantage of that? If you had a Frobenius element, if R squared were a Frobenius element, then when you hit it on I, remember, Frobenius on something looks like the pth power modulo a prime ideal dividing p. So then when you hit it on I, well, because it's R squared, it fixes I, but because it's a Frobenius at a prime ideal, it'll look like I to the p modulo that prime ideal. Now, p is an odd prime. I to the p is, it's either, and p only matters mod 4 as an exponent. I to the p is either I to the first or I to the third. It's either I or minus I. In odd characteristic, I and minus I are definitely not the same thing. X squared plus 1 has distinct roots in odd characteristic, right? X squared plus 1 in characteristic p has distinct roots. So in fact, from the congruence, they actually literally have to be the same number. I to the p cannot be minus I because I cannot be congruent to minus I in OK mod p. In a field of characteristic p, x squared plus 1 cannot have a double root. But once you know those are the same, oh, well, that tells you p is 1 mod 4. On the other hand, if RS or R cubed S is a Frobenius element in this example, then when you hit it on I, it negates, but because it's a Frobenius element, it's going to look like I to the p mod the prime ideal dividing p. And again, the right-hand side is I or minus I, but it can't be I because I and minus I can't be the same in the field of characteristic p when p is odd. And so minus I is I to the p, so p is 3 mod 4. So in fact, we got complementary conditions that they can't overlap. So that's how you can tell them apart. If you fix I and you're a permutation of type 2, 2, if you fix I, then the Frobenius is R squared. But if you negate I, then the Frobenius is RS or R cubed S. Okay? So, so what does that tell us then about, right, so then in the examples we had in the table, the 2 types showed up for 3 and 11 and 17. And since 3 and 11, thus 3 and 11 being 3 mod 4, and the other information tells us that if a prime divides 3 or if a prime divides 11, then the Frobenius at that prime has to be RS or R cubed S. The Frobenius conjugate class of 3 and 11 is the Frobenius conjugate class of 3, and the Frobenius conjugate class of 11 is this conjugacy class. And since 17 is 1 mod 4, and x to the 4 minus 2 mod 17 breaks up into a permutation of cycle type 2, basically similar reasons tell us the Frobenius conjugate class of 17 is R squared. Okay, so that's how we can tell them apart with some extra information. Right. Okay. All right, I'm not going to go through explaining the proof of Dedekind's theorem. I'll write it up in some notes that I'll post and tell you about later today. All right. Now, one thing we haven't met. If we look at the table again, right, 5 is the conjugate class of the 4 cycles, 3 and 11 are conjugate class of RS and R cubed S, but 17 is the conjugate class of R squared S, 7 has Frobenius conjugate class of just S, right? So we've met all the conjugate classes except 1. What haven't we seen so far? Which conjugate class have we not met as a Frobenius? Look at those, huh? Oh, but 1, 3 can't occur, right? Remember we mentioned that. But here are my 5 conjugate classes in the upper left. Which one have we not seen yet? The one what? Yes, the one that fixes all of them, the identity. Okay, so I guess I should also say, you know, the Frobenius at 3, because mod 3, x to the 4 minus 2 mod 3, not mod 3, mod 7, excuse me. Mod 7 is the conjugate class of S and R squared S. You might say, but which one is it? For one prime ideal over 7 is going to be an S, and for another, there's going to be another where it's R squared S. If you have one Frobenius element, you conjugate the prime ideal, you'll get another, and the prime ideal is dividing a prime number, or all conjugate, or all in the same Galois orbit. So, excuse me, are all in the. You can get from one to the other, yeah, by hitting the Galois group. So if one occurs, they'll all occur somehow. So the one thing we haven't found is, what about getting a Frobenius conjugate class that's just 1? What would that mean about x to the 4 minus 2 mod p? How's it going to factor? It's going to have to, mod p will have to split completely. Meaning 4 distinct roots, okay? And when does that happen? Well, I mean, it's not obvious when it happens, but I'll tell you, the first time it happens is 73. Or 89 is the next one, or 113, or 233. Okay? I mean, there's no obvious rule for this. This is just when it happens. Okay? So at these prime numbers, this is when x to the 4 minus 2 breaks into 4 linear factors. So the degree type is 1, 1, 1, 1. And so the Frobenius element at a prime dividing any of these will permute the roots with cycle type 1, 1, 1, 1, meaning it fixes all the roots. Oh, but if you fix all the roots, they generate the field. It's the identity. The Frobenius in these cases will be the identity element in the Galois group. Okay, so now let's use the Chebotarev density theorem. Let's use the Chebotarev density theorem to predict the density of primes where the Frobenius conjugacy class occurs for all the 5 possibilities. Well, can we do it? Excuse me. I wanted to say use Chebotarev to predict the density of primes where. Sorry, I want to say where x to the 4 minus 2 mod p has a specified degree type. So what are the degree types? 1, 1, 1, 1, 1, 1, 2, 2, 2, and 4, right? The first case is split completely. The second one is two linears and a quadratic, irreducible factorization. The third case is two quadratic irreducible factors. And the last case, what does the last case mean? If the degree type is 4. Irreducible, okay? So these are the degree types of the irreducible factorizations. And so the Chebotarev density theorem says, well, we can turn these degree types into a bunch of conjugacy classes that might occur with those degree types. And then Chebotarev tells us how often those Frobenius conjugacy classes occur. So 1, 1, 1, 1, I mean, what's the size of that conjugacy? That just corresponds to the unit conjugacy class. So Chebotarev says the density should be 1/8. Size of the conjugate class, the size of identity divided by the size of the group is 8. What about 1, 1, 2? 1, 1, 2 means, excuse me, 1, 1, 2, that corresponds to which permutation of the roots? 1, 1, 2 is a conjugate class of S, like complex conjugation. How large is the conjugate class containing S? 2. So 2 out of 8. That's the only time it occurs. So that's 2 out of 8, or 1/4. Now, cycle type 2, 2, this is a subtlety. There is not one conjugate class, there are two of them that could occur. So the two conjugate classes are the ones with R squared or RS and R cubed S. So what's the proportion? How many Frobenius? What's the density of primes with Frobenius conjugate class R squared? 1/8. And what about the density of primes with Frobenius conjugate class RS and R cubed S? Yeah, 2, or I'll say 2/8. Makes it easier to add the fraction to the common denominator. So 1/8 plus 2/8 is 3/8. 1/8 plus 2/8. This is 3/8. So this is a little bit of a subtlety here because we're getting two conjugate classes realized in the same kind of factorization. What about the last case, irreducibility? Irreducibility corresponds to a 4 cycle, and which permutations, look at all of them on the right side, which of them is a 4 cycle on the roots? R and R cubed. One conjugacy class can occur with two elements in it. So this will be 2/8 or 1/4. So we see here, using the Chebotarev density theorem, it's going to predict how often x to the 4 minus 2 can occur with a given irreducible factorization. And I made a table here in my notes, x, and I'm going to tell you 1, 1, 1, 1. I put 1, 1, 2, 1, 1, 2, 2, 2, and 4 for various primes up to a given bound. So let's just jump to 10 to the 4 and 10 to the 5. So for 1, 1, 1, 1, the proportion of primes up to 10,000 that have a trivial Frobenius conjugate class divided by the number of primes up to 10,000, the proportion is 0.1163. If you go up to 100,000, 0.1232. For cycle type 1, 1, 2, the proportion is 0.2. I should bring this down a little bit so you can see what the number should be in the limit. 0.2506. Go up to 100,000, 0.2501. For type 2, 2, get 0.3767, 0.3764. And for type 4, we have 0.2554, 0.2501. And in the limit, it should be 1/8, which is 0.125, 1/4, which is 0.25, 3/8, which is 0.375, and another 1/4, which is 0.25. So you see, it looks pretty good. In particular, the density of primes where x to the 4 minus 2 splits mod p. splits is 1/8. And in general, by using the Chebotarev density theorem, you can show that for an irreducible polynomial with integral coefficients, the set of primes P where F mod P splits completely, that's not a phrase, where this splits into distinct linear factors, this has natural density 1 over, oh, I can't say 1 over n because I just use n as a subscript. Darn, 1 over m, where m is the size of the Galois group. Even if your polynomial roots individually don't generate splitting, the size of the Galois group of the splitting field of F over Q. So let me show you, so we can statistically guess how big a Galois group is without having to calculate it. So we'll end with this example. Let's take the polynomial x to the 4 plus 8x plus 12. It's irreducible, okay? Its discriminant is 2 to the 12 times 3 to the 4. And so you can set a computer to work to figure out for different x how many primes up to x have this polynomial split completely. And you go through like starting at 1,000, 10,000, 100,000, a million, and you look at the density, the number divided by the number of primes up to x, and this should tend to a reciprocal integer. And if we start at 10 to the 30, 0.0714, 0.0805, 0.0818, 0.0830. And if you reciprocate, you get 14, 12.41, 12.21, 12.04. So what's your guess? We guess the size of the Galois group of this polynomial should have what size? 12. And in fact, the Galois group is in fact a 4. Okay, so that's impressive that without calculating the Galois group, but just factoring the polynomial and seeing how often it splits, you can guess the size of the group, except we don't have an error term in the Chebotarev density theorem yet. So if only we had that, then maybe we could definitively say with enough statistics, we could pin down, we know it's a reciprocal integer, we could pin down that we know for sure the size of the group. Then we can hunt around and try to compute the Galois group, okay? So next time we'll discuss some more fancy applications of the Chebotarev density theorem, but this is a pretty impressive one to Galois theory statistics, so I'll stop there. Thanks.